Everything began with a single, unfathomable spark. We are going back to the very first particles, the fundamental seeds from which all of reality grew. This journey covers 30 mind-bending theories, from the mathematically rigorous to the wildly speculative, that explain how existence ignited. By the end, you will understand the profound contenders for the universe's very first building blocks. We will explore how a cosmic singularity could birth everything, and whether our entire universe is just a projection from a two-dimensional boundary. Which of these fundamental ideas about our origins intrigues you the most? The universe was born from a point of infinite density and heat. This is the cornerstone of the Big Bang theory, the moment our cosmic clock started ticking. Picture every single bit of matter and energy that would ever exist, from the farthest galaxy to the screen you are looking at now, crushed into a volume smaller than a single atom. This is the singularity, a state so extreme that the very laws of physics as we know them cease to function. According to Einstein's theory of general relativity, such a point of infinite density is where our mathematical descriptions of gravity simply break down. It is the ultimate edge of our understanding. From this incomprehensible beginning, the story of the first particles unfolds. An expansion faster than light itself began. As the newborn universe swelled and cooled, the primordial energy of the singularity began to condense, coalescing into the very first subatomic particles. Quarks and electrons, the fundamental building blocks of everything we see, flickered into existence from the cooling fireball. This theory provides the foundational canvas for all other ideas about particle genesis. Even with its limitations, like the mystery of what triggered the expansion or what existed before the singularity, it remains the starting point for our entire cosmic origin story. Yet that initial fireball presents a deep mystery. Why does our universe look so remarkably uniform in every direction? If you peer into the depths of space with a powerful telescope, the cosmic microwave background, the afterglow of the Big Bang, appears almost identical whether you look left or right. This presents a cosmic conundrum known as the horizon problem. Distant regions of the universe should never have had time to exchange heat and reach the same temperature unless something extraordinary happened in the first fraction of a second. This is where Alan Gough's revolutionary theory of cosmic inflation comes into play. He proposed that before the hot, dense Big Bang we often picture, the universe underwent a breathtakingly brief period of hyper-accelerated expansion. In less than a trillionth of a trillionth of a trillionth of a second, a patch of space smaller than a proton was stretched to a size larger than our entire observable universe today. This exponential growth was driven by a hypothetical energy field, the inflaton field, which filled all of space. Think of it like a strange, cosmic repulsive gravity, pushing space itself apart at a speed far exceeding light. The engine of this expansion was its associated particle, the inflaton. As this inflaton field eventually decayed, it released its immense pent-up energy, flooding the universe with the hot particle soup of the traditional Big Bang. But inflation did more than just stretch space. It also magnified the tiny, random quantum jitters that are inherent to all fields. These microscopic fluctuations, stretched to cosmic proportions, became the seeds for all future structure. The slight variations in density created the gravitational blueprint for everything to come, the galaxies, the stars, and the planets. Without these quantum fingerprints blown up by inflation, the universe would be a vast, dark, and empty sea of uniform gas. Inflation elegantly solves other puzzles too, like the flatness problem, which asks why the geometry of our universe appears so perfectly balanced. By stretching space to such an incredible degree, inflation flattened it out, just as blowing up a balloon makes its surface appear flatter and smoother. While we have not yet directly detected the inflaton particle, the theory of inflation remains a cornerstone of modern cosmology. providing our most compelling explanation for how our structured universe began. But this story of inflation and the Big Bang still leaves a deeper frontier untouched. To find the true origin of the first particles, we must venture even further back, into a realm so extreme it defies our current understanding of physics. This is the Planck Epoch, the first 10 million trillion trillionths of a second after the universe began. In this fleeting, unimaginable moment, all four fundamental forces were one. Gravity, the force that shapes the cosmos, was not separate from the electromagnetic force or the strong and weak nuclear forces. They were fused into a single, unified superforce. At these energies, the very fabric of space-time ceases to be smooth and continuous. Instead, it becomes a seething, frothing foam, quantized into its tiniest possible components. This is the domain of quantum gravity, where the rules of Einstein's general relativity, which govern the large-scale universe, collide with the bizarre probabilistic laws of quantum mechanics that rule the subatomic world. Within this chaotic foam, the first true particles may have been entities of pure geometry, like hypothetical Planck particles, with a mass so immense that their gravitational influence is as strong as the other fundamental forces. To grasp this scale, a single Planck particle would be so dense that it would collapse into a black hole smaller than an atom. This is why the Planck Epoch is currently a black box for our science. The energy required to probe it is over a quadrillion times greater than what our most powerful particle colliders can produce. Unlocking the secrets of this first moment is the ultimate goal for physics, the holy grail that would finally weave together our understanding of the very large and the very small into a single coherent theory of everything. Even as the chaotic foam of the Planck Epoch began to settle, a new chapter of cosmic order was unfolding. The universe entered a phase of breathtaking unity known as the grand-unification epoch. For a fleeting sliver of time after the Planck moment, three of the four fundamental forces were not separate entities at all. The strong nuclear force that binds atomic nuclei, the weak force responsible for radioactive decay, and the electromagnetic force that governs light and chemistry were all one and the same, a single, elegant superforce. This grand unified force was mediated by a new class of particles, hypothetical behemoths called X and Y bosons. These were not like the familiar photons or gluons we know today. They were unimaginably heavy, trillions of times more massive than a proton, and they possessed a truly revolutionary property. They could turn matter into antimatter, and crucially, they could make quarks, the building blocks of protons and neutrons, transform into leptons like electrons. This meant that a single X boson could cause a proton, long thought to be stable, to decay. A proton could spontaneously fall apart, transforming into lighter particles like a positron and pions. This process of proton decay, if it occurs, would be incredibly rare, which is why our own bodies are not disintegrating. But in the extreme energy of the early universe, these X and Y bosons were abundant, orchestrating a frenetic dance of creation and destruction. This dance, however, was not perfectly symmetrical. The decay of these heavy bosons appears to have favored the production of matter over antimatter by just 1 part in a billion. For every billion antiparticles annihilated with their matter counterparts, one single particle of matter was left over. That tiny, almost insignificant surplus is everything. It is every star, every planet, and every one of us. Without that 1 in a billion asymmetry, all matter and antimatter would have completely annihilated each other, leaving behind a universe of pure, featureless light. Physicists have proposed various mathematical frameworks, known as grand unified theories or GUTs, to describe this epoch. Models like SU5 and SO10 are like different blueprints for this fundamental unity, each predicting a unique family of these super-heavy particles that exist at energy scales so high we can only dream of recreating them. They represent a profound step toward a complete theory of everything, a glimpse into a time when the universe's forces were one, and a single, broken symmetry wrote the recipe for all existence. That 1 in a billion surplus of matter was the ultimate cosmic victory, but the question of where the first particles themselves came from might have an even more exotic answer. What if the fundamental seeds of matter were not born from a smooth field, but from the violent death throes of the universe's smallest monsters? This is the theory of primordial black holes. In the unimaginable density of the early universe, mere instants after the Big Bang, the fabric of reality was not perfectly smooth. It was rippling with intense quantum fluctuations. During the period of cosmic inflation, these tiny ripples in the density of space could have been stretched and magnified. Some regions could have become so overwhelmingly dense that they collapsed directly under their own gravity, not into stars or galaxies, but into countless micro-black holes, some no larger than a single proton. These would not be the black holes formed from dying stars we know today. They were primordial, forged in the furnace of creation itself. And according to Stephen Hawking's brilliant work, black holes are not entirely black. He predicted that due to quantum effects at the very edge of their event horizons, black holes should slowly leak radiation. This Hawking radiation causes them to lose mass and over astronomical timescales completely evaporate in a final explosive burst. For a stupendously small primordial black hole, its entire lifetime could be a fleeting flash. In that final instant of evaporation, it would release all of its energy back into the universe as a shower of particles and radiation. In this breathtaking scenario, the very first particles we recognize, like quarks and electrons, could have been the final whispers of dying micro-black holes. They were not the starting point of creation, but the end product of a prior, more exotic existence. This leads to a profound modern possibility. What if not all of these primordial black holes evaporated? Those that formed with slightly more mass could still be with us today, drifting unseen through the cosmos. Because they do not emit light, they would be virtually invisible. This makes them a compelling candidate for the mysterious substance known as dark matter. The gravity of countless primordial black holes could be the hidden glue holding galaxies together. The hunt for them is now a major scientific endeavor. Astronomers look for subtle clues, like the way their gravity can briefly bend and magnify the light from distant stars, an event called microlensing. Finding one would not just solve the dark matter puzzle, it would open a direct window back to the universe's first moments, revealing a time when reality was sown with tiny, dark seeds. But that cosmic dawn of matter and force was still a universe of pure, weightless energy. For the first particles to build anything lasting, they needed a property we take for granted: mass. The mechanism that gave them this gift is tied to one of the most pivotal events in cosmic history, the breaking of electroweak symmetry. In the universe's first trillionth of a second, the electromagnetic force and the weak nuclear force were not separate. They were two facets of a single, elegant electroweak force. Particles like the photon, which carries light, and the W and Z bosons, which mediate radioactive decay, were all identical, massless entities racing through the cosmos at the speed of light. But as the universe expanded and cooled, it underwent a profound phase transition, much like steam condensing into water. This change was triggered by a field that permeates all of space, the Higgs Field. Imagine the entire cosmos suddenly filling with an invisible, treacle-like substance. Before this moment, particles like the electron and the quarks that make up protons moved freely without mass at the speed of light. But as the Higgs field switched on, it began to interact with them. Some particles, like the photon, passed through this cosmic treacle completely unaffected, remaining massless. Others, like the W and Z bosons and the fundamental fermions, began to slog through it, and this resistance is what we experience as their mass. The more a particle interacts with the Higgs field, the heavier it is. This process is what gave the W and Z bosons their immense mass. effectively splitting the weak nuclear force apart from the electromagnetic force and creating the four distinct forces we observe today. The discovery of the particle associated with this field, the Higgs boson, was a monumental achievement. In 2012, scientists at the Large Hadron Collider announced they had found it, a fundamental excitation in the Higgs field that confirmed a theory nearly 50 years old. This was not just about finding another particle. It was about validating the very mechanism that allows our universe to have substance. Without the Higgs field giving mass to electrons, atoms could not form. Without mass for the quarks, protons and neutrons would not exist. There would be no chemistry, no planets, no life. This single event of symmetry breaking was the cosmic switch that transformed a sea of radiant energy into a universe capable of building complex structures, including us. That tiny 1 in a billion surplus of matter is the most important number in our existence, but its origin remains one of the greatest puzzles in physics. Why is the universe made of something instead of nothing? This is the problem of baryogenesis, the genesis of baryonic matter, the protons and neutrons that form the nuclei of atoms. In the 1960s, the physicist Andrei Sakharov laid out 3 essential conditions that must be met for a universe to create more matter than antimatter. First, there must be a process that does not conserve baryon number. This means the total amount of matter in the universe cannot be a fixed, unchanging quantity. There must be a way to create it from a state of balance. Second, there must be a violation of both charge and parity symmetry. This is a profoundly strange requirement. It means that the laws of physics must treat matter and antimatter slightly differently, and they must also distinguish between right-handed and left-handed particles. The universe, at its most fundamental level, must have a slight preference, a built-in bias. Third, these processes must occur out of thermal equilibrium. They cannot happen in a calm, settled state where every reaction is perfectly reversible. They require a sudden, dramatic shift in the environment, like the rapid cooling of the early universe, to lock in the asymmetry and prevent it from being erased. Grand unified theories with their X and Y bosons provide one possible pathway, but there is another elegant and compelling idea. Leptogenesis proposes that the matter asymmetry actually began not with quarks but with neutrinos. This theory introduces a hypothetical heavy particle, a right-handed neutrino. In the early universe, these incredibly massive neutrinos were abundant. As they decayed, they did not produce equal amounts of particles and antiparticles. Due to the violation of charge and parity symmetry, their decay favored the production of ordinary, left-handed neutrinos over their antimatter counterparts. This created a fundamental lepton asymmetry, an imbalance in the number of leptons, the family that includes electrons and neutrinos. Then, through a subtle and complex process involving the weak nuclear force, this lepton asymmetry was converted into the baryon asymmetry we observe today. The slight excess of neutrinos was transformed into the slight excess of quarks that built our world. This means the very first particles, the quarks and electrons that coalesced after the Big Bang, already carried the imprint of this ancient cascading imbalance. The existence of every atom in your body is a direct consequence of a preference written into the decay of a ghostly, super-heavy neutrino in the universe's first moments. Without that specific, biased decay in a cooling, non-equilibrium environment, the cosmos would be a dark, empty void. Our existence hinges on a broken symmetry that favored one type of particle over another, a fundamental cosmic prejudice that made all the difference. That fundamental cosmic prejudice, however, leads us to a deeper layer of mathematical beauty and mystery. For decades, physicists have been troubled by a question known as the hierarchy problem. Why is gravity so unimaginably weaker than the other fundamental forces? The mass of the Higgs boson is precariously balanced, and according to our current theories, quantum fluctuations from the highest energy scales should make it astronomically heavier, tearing apart the delicate structure of our universe. An elegant solution to this conundrum is a principle called supersymmetry. This theory proposes a profound and beautiful symmetry of nature, a kind of cosmic partnership. For every known particle of matter, every fermion like the quark and the electron, there exists a superpartner, a boson. And for every force carrier, every boson like the photon and the gluon, there exists a superpartner, a fermion. This would double the number of elementary particles in our cosmic inventory. The electron would be paired with a selectron, quarks would be partnered with squarks. The photon's partner would be the photino, and the Higgs boson's partner would be the Higgsino. In a perfectly supersymmetric universe, these particles would have the exact same mass as their ordinary counterparts. This symmetry is the key to solving the hierarchy problem. The quantum contributions from these superpartners would perfectly cancel out the troublesome fluctuations that threaten to inflate the Higgs mass, providing a natural and stable explanation for the world we see. In the fiery conditions of the very early universe, these particles would have been abundant, colliding and transforming in a complex dance. As the cosmos cooled, however, this perfect symmetry would have been broken. The superpartners we predict today are not massless twins. They must be incredibly heavy, which is why our most powerful particle colliders have not yet created them. This breaking of supersymmetry gives rise to a remarkable consequence. The theory predicts that the lightest of these superpartners, often called the lightest supersymmetric particle or LSP, would be stable. It cannot decay into anything else because it must conserve a quantum property that all particles share. A leading candidate for this stable particle is the neutralino, a neutral mixture of the superpartners of the Higgs boson and the Z boson. This particle would not interact through the electromagnetic or strong nuclear forces. It would be massive, stable, and essentially invisible, passing through ordinary matter like a ghost. This sounds familiar, doesn't it? It has all the properties required for dark matter. Supersymmetry, therefore, offers a stunning two-for-one deal. It stabilizes the very fabric of our particle physics while simultaneously providing a perfect, compelling candidate for the mysterious substance that makes up most of the matter in the cosmos. The continued search for these shadow particles is one of the most exciting quests in modern science. Finding just one would not only complete our picture of the early universe's particle zoo, it would validate a symmetry so deep and powerful that it might be woven into the very geometry of spacetime itself. Supersymmetry offers a breathtaking expansion of our cosmic family, but it still treats particles as infinitesimal points. To solve the deepest riddles of gravity and the Big Bang Singularity, we must fundamentally change what a particle is. This is the radical proposal of string theory. It suggests that at the heart of every electron and every quark is not a zero-dimensional dot, but a tiny, vibrating loop or strand of energy, a string. These strings are unimaginably small on the scale of the Planck length. If an atom were magnified to the size of our solar system, a single string would be no larger than a tree on Earth. The magic lies in their vibration. Just as a single violin string can produce different notes depending on how it is plucked, a single fundamental string can manifest as different particles based on its unique resonant frequency. One vibrational pattern gives rise to an electron. A different, higher energy pattern creates a quark. Another distinct vibration produces a photon. In this elegant framework, all the forces and all the matter in the universe are composed of the same underlying substance, simply humming different cosmic melodies. This is the ultimate unification, a theory of everything where the particle zoo is really a symphony orchestra. For this mathematical symphony to be consistent, however, the strings cannot vibrate in just the three spatial dimensions we experience. The equations of string theory only work in a universe with extra dimensions of space. Not just one or two, but 6 or 7 additional spatial dimensions, curled up into shapes so tiny we never notice them. Think of a long, thin garden hose. From a distance, it looks like a simple one-dimensional line. but if you get very close, you see its surface is a two-dimensional cylinder with one of those dimensions curled into a small circle. String theory proposes that at every point in our three-dimensional space, there exist 6 or 7 more dimensions, compactified into intricate, complex shapes known as Calabi-Yau manifolds. The specific geometry of these hidden dimensions determines the properties of our universe, fixing the masses of particles and the strengths of the forces. This leads to a profound new vision of the Big Bang itself, a model called string gas cosmology. In this picture, the early universe was a hot, dense gas of these fundamental strings, winding and moving through all 9 or 10 spatial dimensions. The initial singularity, that point of infinite density where physics breaks down, might never have occurred. Instead, the universe could have emerged from a previous phase, perhaps even a bounce from a prior cosmic contraction. The strings, with their extended nature, could have prevented the infinite densities that plague point particle theories. As this string gas cooled and the extra dimensions stabilized, our 3 familiar dimensions expanded dramatically, while the others remained tightly wound, setting the stage for the universe we observe. String theory transforms our quest for the first particles from a search for dots into a search for the universe's first notes, the primordial vibrations that wrote the score for all of reality. String theory's hidden dimensions open the door to a possibility even more profound than a single beginning. Our Big Bang may not have been the universe's first and only dawn. In the ekpyrotic-universe model, the cosmic genesis we observe was the result of a cataclysmic collision in a higher dimensional reality. The name itself comes from the Greek word for conflagration, a great fire. Here, our entire three-dimensional universe is not all there is. It is a three-dimensional membrane, or brain for short, existing within a vast higher dimensional space known as the bulk. Floating in this bulk is another parallel three-dimensional brain. Imagine 2 immense, perfectly flat sheets of reality, separated by a tiny gap. These 2 brains are drawn together by a force, moving slowly and then colliding with unimaginable force. That collision, that moment of impact, is what we perceive as the Big Bang. It was not an explosion from a single point, but a universe-wide ignition event, transferring an immense amount of energy into our brain. This collision did not create matter and energy from nothing. It simply converted the kinetic energy of the moving brains into the hot, dense plasma of particles that would become our cosmos. This scenario elegantly avoids the troubling singularity, that point of infinite density where physics breaks down. The Big Bang was not the beginning of time and space, but a violent transition from a prior state. The model is often cyclic. After the collision, the brains bounce apart, stretch and cool, and are then slowly drawn together again by an attractive force, setting the stage for the next collision and the next cosmic cycle. This process could repeat forever, with no true beginning or end. During the moment of collision, quantum fields on the brains were violently shaken. This jolt created fluctuations, tiny ripples in the fabric of our brain. As the brains separated and our universe began its expansion, these ripples were stretched, becoming the seeds for all future structure. The ekpyrotic model naturally produces a spectrum of perturbations that is nearly scale invariant, meaning it looks the same on all distance scales, perfectly matching the patterns we see etched into the cosmic microwave background. As for the first particles, their production was direct and dramatic. The immense energy of the collision heated our brain to an incredible temperature, spontaneously creating a dense soup of quark-gluon plasma, the precursor to all atomic matter. There was no need for a separate episode of inflation to create this hot state. The brain collision itself provided the heat and the initial conditions. The resulting thermal history of the universe then proceeds much like the standard Big Bang model, but with a completely different origin story. This idea reframes our entire cosmic history, suggesting our universe is just one page in an infinite cosmic storybook, with each Big Bang a new chapter born from a collision of worlds we cannot see. While string theory adds extra dimensions, another path to quantum gravity takes a radically different approach by reimagining the very fabric of space and time. This is loop quantum gravity, a theory that suggests spacetime is not a smooth, continuous backdrop, but is instead woven from a discrete, granular structure. Picture the universe not as a blank canvas, but as an incredibly fine, shimmering fabric made of indivisible threads, each a billion trillion times smaller than an atom. These loops of gravitational field woven into a network form the quantum geometry of space. Area and volume come in tiny, discrete packets, a pixelation of reality at the smallest possible scale. This fundamental graininess has a profound consequence for the origin of the universe. It means there is a limit to how much matter and energy can be squeezed into a single point. In loop quantum cosmology, the sibling of this theory, the Big Bang Singularity, simply cannot exist. Instead of a mysterious point of infinite density, our universe emerged from a great cosmic rebound, a big bounce. Before our expanding phase, there was a previous universe that was contracting. As it collapsed, the density and temperature rose to incredible levels, but the quantum nature of spacetime prevented it from reaching infinity. The repulsive force generated by the quantum geometry became so powerful that it overcame the pull of gravity, causing the universe to bounce back and begin the expansion we see today. Our Big Bang was not a beginning from nothing, but a transition from a prior cosmic phase. During this bounce, the universe would have been filled with an ultra-hot, dense state of matter and radiation. The violent quantum gravitational effects would have shaken the very foundations of spacetime, generating fluctuations that rippled through all the fundamental fields. These ripples would have been the seeds for the first particles, a burst of creation as the universe rebounded. Quarks, electrons, and photons would have been copiously produced as the quantum geometry relaxed, setting the stage for the hot Big Bang plasma. This leads to a stunning, testable prediction. The quantum fluctuations from the bounce would leave a specific imprint on the oldest light in the universe, the cosmic microwave background. Unlike inflation, which predicts a nearly perfect Gaussian distribution of these fluctuations, a bounce could leave a distinct non-Gaussian signature. It might also create a unique pattern of gravitational waves, a primordial rumble that future space-based observatories could potentially detect. Finding such a fingerprint would not just confirm an alternative to inflation. It would revolutionize our understanding of cosmic origins, revealing that our universe is part of an endless cycle of contraction and rebirth, with each bounce writing its signature into the first particles of a new dawn. This cosmic cycle of bounces and collisions hints at a reality far grander than our own universe. Our entire cosmic history, from the first particles to the last stars, may be just one small pocket in an infinite, ever-expanding megaverse. This is the theory of eternal inflation. Picture the initial inflationary field not as a single event that started and stopped, but as an unstoppable engine of creation. In most regions, the inflattened field decays, releasing its energy to form a hot Big Bang universe like our own. But due to quantum fluctuations, some regions of this inflating space never settle down. In these patches, the inflationary field retains its high energy, causing space to expand exponentially faster than the surrounding areas. These runaway regions become vast, inflating seas, while within them, quantum drops continually condense out, each one a new bubble universe. Our entire observable cosmos is one such bubble, floating in an unimaginably vast, eternally inflating background. The critical point is that when each bubble forms, the process of its nucleation can randomly determine the local laws of physics. The way the Higgs field settles, the strengths of the fundamental forces, even the number of spatial dimensions that stabilize, all of this can be different from one bubble to the next. In one universe, the weak nuclear force might be so strong that hydrogen fuses instantly, preventing stars from ever forming. In another, the electron might be 100 times heavier, making chemistry impossible. The specific particles that emerged in our universe, the quarks and electrons with their precise masses and charges, are not a unique, inevitable outcome. They are simply the winning ticket in a cosmic lottery, the random set of physical constants that allowed for the emergence of complex structures and, ultimately, observers like us. This is where the anthropic principle enters the discussion. It is not an explanation, but a selection effect. We should not be surprised to find ourselves in a universe capable of supporting life, because in the vast and varied landscape of the multiverse, only such hospitable bubbles can ever give rise to beings who can ask the question. The first particles in our story were not the only possible first particles. They were simply the ones that appeared in our particular bubble, perfectly tuned by chance to build the world we see. This idea transforms our quest from a search for a single, fundamental theory of everything to a mapping of a vast landscape of possibilities, where our existence is both profoundly special and utterly mundane. Yet this endless multiverse of possibilities still operates within a single, overarching timeline. What if time itself is cyclical and our universe's death is not an end but a prelude to another beginning? This is the heart of Roger Penrose's conformal-cyclic-cosmology, a theory as elegant as it is audacious. It proposes that our universe is just one eon in an endless chain with no true beginning and no final end. The key to this cosmic cycle lies in a mathematical concept called conformal symmetry. At the very end of time, when the universe has expanded to near emptiness and all matter has decayed away into radiation, something remarkable happens. The universe becomes vast, cold, and simple. With no massive particles left to define a scale, the concepts of distance and size lose their meaning. In this state of pure, featureless light, the geometry of the universe becomes conformally equivalent to the hot, dense singularity of the Big Bang. It is a different kind of sameness, a mathematical reset where the immense, empty future and the infinitesimally small past are, in essence, identical. The end of one eon seamlessly becomes the Big Bang of the next, but how could anything possibly carry over from one eon to another? Information, it seems, might find a way. Penrose suggests that the gravitational energy from colossal collisions in a previous eon, like the mergers of supermassive black holes, could leave imprints on the new one. These imprints would manifest as faint, circular patterns in the cosmic microwave background, known as Hawking points. They are named for Stephen Hawking, as they are theorized to be the final evaporation of primordial black holes from the eon before ours, their last whisper imprinted onto the dawn of our own universe. If we could decode these faint rings in the sky, they would be messages from a dead cosmos, a fossil record written in gravity. What would the first particles of a new eon inherit from their predecessors? They would not be the same atoms or molecules, as all structure is erased in the great conformal transition. Instead, they might carry the subtle gravitational memory of a universe that came before. The initial distribution of matter and energy in our own Big Bang could have been subtly shaped by the gravitational waves that rippled across the boundary between eons. This means the very first quarks and electrons that condensed in our cosmic dawn might have been seeded by the dying echoes of a previous reality. This idea reframes the ultimate fate of our universe. The heat death, often seen as a bleak and final oblivion, is instead a cosmic chrysalis. The dissolution of all structure is not an erasure, but a necessary purification, a return to a state of symmetrical perfection from which a new, vibrant universe can be reborn. Our entire cosmic story, from the first particle to the last photon, becomes a single chapter in an infinite book, with each ending perfectly setting the stage for a new beginning. The endless cycle of eons suggests a universe built on information, but that information might be stored in a place we would never expect. Our three-dimensional reality, with its galaxies, stars, and planets, could be a magnificent illusion, a holographic projection from a two-dimensional surface at the edge of the cosmos. This is the holographic principle, and its origins lie in the paradoxical physics of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's event horizon has entropy, a measure of its information content. Astonishingly, the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its horizon. This was bizarre, as in our everyday experience, information storage capacity scales with volume like the memory in a computer chip. For a region of space to have its information encoded on its boundary seemed to violate common sense. Physicists Gerard T. Hooft and Leonard Susskind took this idea and ran with it, proposing that this was not just a quirk of black holes, but a fundamental property of the universe. The holographic principle states that all the information describing the interior of a region of space, every particle, every force, is entirely encoded on its lower dimensional boundary. A star, a planet, and you are, in a sense, a complex pattern of data painted onto the cosmological horizon. Imagine watching a breathtakingly realistic three-dimensional movie. The entire experience, every depth and detail, is actually contained on a flat, two-dimensional screen. The holographic universe is a similar concept, but for reality itself. If this is true, then the particles we think of as fundamental are not the bedrock of reality. Quarks, electrons, and photons are not tiny dots, but emergent phenomena. They are like pixels in a cosmic display, their properties and interactions arising from the way information is processed and projected from the distant two-dimensional surface. This has a staggering implication for the origin of the first particles. In the very early universe, the cosmological horizon was incredibly close. The entire observable universe was a tiny, hot region. According to the holographic principle, the information for everything within that region was encoded on its boundary. As the universe expanded, that boundary stretched and the information on it evolved. The first particles that condensed out of the Big Bang fireball were not the starting point. They were the three-dimensional manifestation of a quantum computation happening on the edge of space. Their properties, their masses, their charges were all determined by the way bits of information were arranged on that primordial screen. This transforms our search for the first particles from a hunt for objects to a deciphering of a cosmic code. The fundamental question is no longer what are particles made of, but what information describes them. The holographic principle suggests we are living in a universe where the deepest level of reality is not made of stuff, but of bits, and the first particles were simply the first lines of code executed in the grand simulation of existence. A universe where the strong nuclear force was not perfectly symmetric would look profoundly different from our own. This is the heart of the strong CP problem, one of the most puzzling fine-tunings in all of physics. CP stands for charge and parity, a combined symmetry that swaps a particle for its antiparticle and also mirrors its spatial coordinates. We know the weak nuclear force violates this symmetry, which was crucial for creating the matter-antimatter imbalance. Yet, for the strong force that binds atomic nuclei, this symmetry appears to be perfectly, inexplicably preserved. The equations of quantum chromodynamics, our theory of the strong force, naturally allow for a term that would violate CP symmetry. This term would cause the neutron, for instance, to have a measurable electric dipole moment, a slight separation of positive and negative charge that would make it behave like a tiny cosmic compass. Experiments have searched for this effect with incredible precision, but the neutron's electric dipole moment is zero for all practical purposes. The fundamental constant that controls this CP violation, known as the theta angle, appears to be tuned to zero with an accuracy of 1 part in a billion. The universe seems to have chosen a very specific, highly unlikely value for no apparent reason. This is the strong CP problem, a mystery that suggests a piece of physics is missing from our picture. The most elegant solution was proposed by Roberto Pexi and Helen Quinn. They suggested that this theta angle is not a fixed constant at all, but a dynamic field that permeates all of space. Just as the Higgs field gives particles mass, this new field would naturally relax to a value of 0, effectively solving the strong CP problem and explaining why the strong force is so symmetrical. The excitation of this field, its fundamental ripple, is a hypothetical particle called the action. The action is predicted to be incredibly light, potentially millions of times lighter than an electron, and exceptionally shy, interacting only very weakly with ordinary matter. In the early universe, as it cooled through a critical temperature, the Peck-Quinn field would have frozen into a random value, like a needle on a cosmic dial settling on a random number. As the universe continued to expand, this field began to oscillate around its preferred minimum value of 0. These cosmic oscillations are the action field ringing like a bell. And just like any vibrating field in quantum mechanics, these oscillations manifest as particles. This is the misalignment mechanism, and it would have produced a staggering number of actions, an invisible cold fog filling all of space. Because they were born cold and moving slowly without the intense thermal energy of the hot Big Bang plasma, these actions are a perfect candidate for dark matter. They would not clump tightly like ordinary matter, but would form a diffuse, gravitational scaffold that guides the formation of galaxies. Their collective mass from the sheer number of particles produced could account for the missing 85% of the matter in the cosmos. The hunt for these ghostly particles is underway in laboratories around the world. Experiments like the Action Dark Matter Experiment, or ADMX, use powerful superconducting magnets to create a magnetic field that, in theory, should convert invisible actions from the galactic halo into detectable microwave photons. It is like tuning a cosmic radio to a specific station, hoping to hear the faint whisper of a particle that solved a profound symmetry problem and then went on to build the cosmic architecture we see today. Finding the action would be a monumental double discovery, resolving a deep theoretical puzzle while simultaneously illuminating the dark heart of the universe. The discovery of the Higgs boson felt like an ending, a final piece placed in the grand puzzle of the Standard Model. But what if that piece is not what it seems? What if the Higgs is not an elementary, fundamental particle, but a composite entity, a cosmic smoke screen hiding a deeper layer of reality? This is the provocative proposal of Technicolor theories. They challenge the very nature of the Higgs mechanism by suggesting that the agent giving mass to the universe is not a lone field, but a bound state of new, more fundamental particles. In this picture, the Higgs boson is not a simple dot. It is a meson, a particle analogous to the pions in our own atomic nuclei, but built from something entirely new. These constituents are called technetiumines, and they feel a new, powerful force, the Technicolor force, which is a super strong version of the strong nuclear force that binds quarks together. In the early universe, this Technicolor force caused technetiumines and their antiparticles to condense into pairs, much like quarks condense to form protons and neutrons. This condensation, this dynamical binding, is what spontaneously broke the electroweak symmetry. There was no fundamental Higgs field turning on. Instead, the collective behavior of this hidden technimatter generated the resistance we interpret as mass. The process is called dynamical electroweak symmetry breaking, and it is a far more mechanical, almost architectural way of building mass into the universe. Just as the strong force gives rise to a whole zoo of composite particles like pions and rhos, the Technicolor force would produce its own exotic family. We would expect to see technetiumines, some of which might be massless goldstone bosons that get absorbed to give mass to the W and Z bosons. We would also predict heavier resonances, the technerhos, which would be the heavy cousins of the particles we see in our own particle colliders. So why has this elegant idea fallen out of favor? The devil is in the details. The simplest Technicolor models made predictions that have been ruled out by experiment. They tended to predict large corrections to the masses of the W and Z bosons that we simply do not see. They also struggled to generate the correct masses for the known fermions like the quarks and electrons without introducing overly complex and fine-tuned additional mechanisms. The beautiful simplicity of the original idea became mired in complications, yet the core concept remains profoundly intriguing. It offers a path to a universe without fundamental scalar fields, which many theorists find more natural. The Higgs boson, in this view, is just the tip of a vast hidden iceberg of technimatter and new strong forces. Its discovery may not have closed the book on particle physics, but merely opened a new chapter, one where the most familiar forces in our world emerge from a shadow world of unimaginable strength. The force of gravity feels so weak because its true strength is leaking away. While electromagnetism and the nuclear forces are confined to our three-dimensional brain, gravity can seep into the vastness of higher dimensional space. This is the radical solution to the hierarchy problem proposed by the Randall-Sundrum model, a warped geometry where our universe is a membrane floating within a five-dimensional bulk. In this setup, the weakness of gravity is not a fundamental property, but an illusion caused by our position in the higher dimensional landscape. We experience only a faint shadow of gravity's full intensity. This warping of space also has a direct and stunning consequence for the particle zoo. If extra dimensions are real, then the particles we know and love are not the whole story. Each one, from the humble electron to the lofty Higgs boson, could have an infinite series of heavier twins. These are known as Kaluza-Klein particles. Think of a guitar string. It can vibrate in its fundamental mode, producing the lowest note, but it can also vibrate in higher harmonics, creating a series of overtones. A standard model particle is like that fundamental note, the lowest energy vibration of a field that exists throughout all dimensions, including the compactified ones. But that field can also vibrate in more complex patterns within the tiny, curled-up extra dimensions. Each of these higher frequency vibrations manifests in our three-dimensional world as a new, distinct particle with the same electric charge and other quantum numbers as its lighter sibling, but with a vastly greater mass. This forms a Kaluza-Klein tower, an infinite ladder of progressively heavier copies. In the extreme heat of the early universe, these towers would have been fully populated. The immense energy of the Big Bang fireball would have excited these higher harmonics, creating a brief, dense plasma of both ordinary particles and their heavy Kaluza-Klein partners. As the universe expanded and cooled, however, these massive copies became unstable. They rapidly decayed back down the tower, cascading into the lightest particles and leaving behind only the fundamental modes we observe today. But the lightest Kaluza-Klein particle in some theories could be stable, making it another compelling candidate for dark matter. The search for these echoes of extra dimensions is a primary goal of modern particle physics. If they exist, we could produce them in powerful colliders like the Large Hadron Collider. Their signature would be unmistakable, an event where energy seems to disappear, carried away by an invisible, stable Kaluza-Klein particle, or the sudden appearance of a heavy electron or quark with no standard model counterpart. Finding just one would be the most direct evidence imaginable that our reality is a shadow cast from a higher dimensional world, and that the first particles were merely the opening notes in an infinite cosmic scale. The elegance of supersymmetry comes with a dangerous cosmic consequence. When we embed this beautiful symmetry into a universe governed by gravity, we get supergravity, and with it, a new and potentially catastrophic particle, the gravitino. This is the superpartner of the graviton, the hypothetical particle that carries the force of gravity itself. If the graviton exists, it would be a massless messenger weaving the fabric of spacetime. Its superpartner, the gravitino, is a different beast entirely. It is a fermion, a particle of matter, and it is incredibly heavy. In the seething heat of the early universe, gravitinos would have been produced in abundance. Every collision of high-energy particles in the primordial plasma had a chance to create a gravitino and its antiparticle, a process known as thermal production. This is where the story takes a perilous turn, leading to the gravitino-problem. The fate of the entire cosmos hinges on whether this particle is stable or not, and both possibilities lead to a universe we would not recognize. If the gravitino is unstable, it spells disaster for the formation of the first elements. Imagine a gravitino decaying long after the universe has cooled into a soup of protons and neutrons, but before they can safely fuse into the light nuclei of hydrogen, helium, and lithium. This decay would be violent, releasing a torrent of high-energy photons and other particles that would shred the delicate atomic nuclei as they form. The predicted abundances of these light elements, which perfectly match our astronomical observations, would be completely destroyed. Our universe would not have the right ingredients to build stars or planets. The other option is even more stark. If the gravitino is stable, it becomes a relic, a super-heavy particle left over from the Big Bang. Because it interacts with ordinary matter only through gravity and perhaps the weak force, it would not annihilate away. It would simply hang around, an invisible, massive ghost. The collective weight of these relic gravitinos would be so immense that their gravitational pull would have caused the universe to collapse back on itself in a catastrophic big crunch only a few years after the Big Bang. The cosmos would have ended before the first star ever ignited. Clearly, neither of these scenarios describes our long-lived and structured universe, so a solution must exist. Physicists have proposed several elegant escapes from this cosmological trap. One is to lower the temperature of the universe after inflation. This reheating temperature, which marks the beginning of the hot Big Bang phase, must be kept relatively low to prevent the overproduction of gravitinos in the first place. If the universe was never hot enough to cook up too many of them, the problem is avoided. Another solution lies in the specific way supersymmetry is broken. In some models, the gravitino can be made to be the lightest supersymmetric particle, or LSP. In this case, it becomes stable and, crucially, it is so incredibly light that its total density remains small enough not to overclose the universe. It would then simply become another candidate for dark matter, a ghostly gravitino haze that permeates the cosmos. This delicate balancing act shows just how fine-tuned our cosmic history might be, where the survival of the universe depended on the specific properties and population of a single, elusive particle. The weakness of gravity is not its only puzzling feature. Our magnetic experience of the world is fundamentally lopsided. While electric charges come in positive and negative, freely existing as individual protons or electrons, magnetic poles seem forever locked together. Every magnet, from a simple refrigerator decoration to the Earth itself, has both a north and a south pole. If you were to break a bar magnet in half, you would not get isolated poles. You would simply create two smaller magnets, each with its own north and south. This asymmetry troubled the great physicist Paul Dirac deeply. In the 1930s, he demonstrated that the existence of just a single, isolated magnetic charge, a magnetic monopole, would elegantly explain one of the deepest mysteries in physics, the quantization of electric charge. Why is the charge of an electron exactly equal and opposite to that of a proton? Dirac showed that if even one magnetic monopole existed somewhere in the universe, it would force all electric charges to be integer multiples of a fundamental unit. The universe's love of whole numbers could be a direct consequence of a hidden magnetic particle. Grand unified theories take this elegant idea and supercharge it. They predict that these magnetic monopoles are not just simple particles. They are topological defects, cosmic knots that formed in the fabric of reality during a dramatic phase transition in the very early universe. As the universe cooled and the grand unified force broke apart into the strong and electroweak forces, the underlying field shifted into a new, lower energy state. Picture a vast cosmic pond freezing over on a cold night. As the water turns to ice, bubbles and cracks form. In some regions, the ice crystals align one way, in others, a different way. Where these different domains of alignment meet, a defect, a flaw in the crystalline structure, is trapped. In the cooling universe, these defects were not cracks in ice, but tangled configurations of the Higgs field that describes the broken symmetry. These knots are the magnetic monopoles, and they are monstrous entities. A single GUT monopole would be unimaginably heavy, perhaps 10 million billion times more massive than a proton. It would be so heavy that its mass would be concentrated in a region of space smaller than an atomic nucleus, making it an incredibly dense and exotic object. According to the standard Big Bang model without inflation, these behemoths should have been produced in staggering numbers. The phase transition that created them would have resulted in at least one monopole per horizon volume, the patch of space that could have been in causal contact at that time. Carrying this prediction forward to the present day leads to a cosmic catastrophe. The calculated density of these relic monopoles would be so immense that their collective mass would overwhelm the universe. They would have caused the cosmos to recollapse into a big crunch long before any stars or galaxies could ever form. This glaring contradiction between theory and observation became known as the cosmological monopole problem. Where are all these magnetic monopoles? Our very existence is proof that they are incredibly rare, a fact that for a time threatened to unravel the entire elegant framework of grand unified theories. The solution to this menacing overpopulation came from the same mechanism that solved the horizon and flatness problems, cosmic inflation. Alan Guth originally developed the theory of inflation in part to address this very monopole problem. The period of hyper-accelerated expansion acted as the ultimate cosmic dilutant. Any primordial monopoles that formed before or during the very beginning of inflation would have been flung impossibly far apart from one another as space itself stretched at a phenomenal rate. The density of these defects would have been reduced to virtually zero within our entire observable universe. It is like having a single grain of sand on an entire planet. You would be extraordinarily lucky to ever find it. Inflation thus performs a delicate rescue operation for GUTs. It allows for the elegant prediction of magnetic monopoles without dooming the universe to an early gravitational collapse under their weight. They could exist, but they are now so fantastically rare that finding one is the ultimate needle in a cosmic haystack. The hunt for these legendary particles is more than a quest for a scientific curiosity. It is a direct test of the highest energy physics we can conceive of. Experiments like the monopole and exotics detector at the LHC, known as MO-EDL, are specifically designed to be trapped for these exotic entities. They use stacks of plastic detectors that will be permanently etched by the passage of such an immensely heavy, highly ionizing particle, leaving a track that could not be faked by any ordinary cosmic ray or standard model event. Other searchers scan ancient mica crystals deep underground, looking for damage trails left over millions of years by a slowly moving monopole. Finding just one would be a discovery of Nobel Prize-winning magnitude. It would provide the first direct experimental evidence for grand unified theories, confirm Dirac's profound insight, and offer a tangible relic from a time when the forces of nature were one. The search for the magnetic monopole is a search for a fossil from the universe's first split second, a solitary knot in space-time that holds the key to our grandest unified dreams. That faint echo of creation is not carried by light alone. 1 second after the Big Bang, as the universe cooled enough for atomic nuclei to form, a second, even more elusive relic was set free. This is the cosmic neutrino background, a cosmic sea of the most ghostly particles known to science. Neutrinos had been born in the first instance, created in vast numbers alongside quarks and electrons. For that first second, they were trapped in a constant dance with the dense, hot plasma of particles, constantly scattering off electrons and protons. But as the universe expanded and its density dropped, something pivotal happened. neutrinos, which interact only via the weak nuclear force and gravity, suddenly found themselves unable to find a dance partner. The probability of them hitting another particle plummeted to almost zero. In an event known as neutrino decoupling, they effectively vanished from the rest of the cosmic soup, streaming freely across the expanding cosmos, never to interact significantly with matter again. Today, this primordial sea is unimaginably vast and cold. For every single photon in the cosmic microwave background, there are around 150 neutrinos from this background. They are everywhere, with roughly 1 billion of them passing through your thumb every single second, completely unnoticed. Their temperature is even lower than the microwave background, a frigid 1.95 degrees above absolute zero, a testament to how early they decoupled. While they are ghostly, their collective gravity is not insignificant. This vast, invisible ocean of neutrinos makes up a portion of the cosmic budget of radiation and matter, and their presence influenced how the first structures in the universe could form. In the earliest epochs, these neutrinos were moving at nearly the speed of light. Their high velocity meant they could stream out of regions of slightly higher density, effectively washing out the very smallest gravitational potential wells. This subtle action suppressed the formation of the tiniest clumps of dark matter, which in turn altered the pattern of galaxy formation we see today. The cosmic web of galaxies is in part a fingerprint of this ancient neutrino influence. Detecting these specific 1-second-old neutrinos directly is one of the ultimate challenges in experimental physics. The problem is their incredibly low energy. Modern neutrinos from the sun or from nuclear reactors are millions of times more energetic than these primordial ones. Our current detectors are completely blind to such faint whispers. Catching one would be like trying to hear a single snowflake land in the middle of a hurricane. Future proposals are breathtakingly ambitious. One idea involves using a giant sphere of solid helium, cooled to near absolute zero, as a target. If a primordial neutrino were to very rarely interact with the nucleus of a helium atom, it would deposit a minuscule amount of energy, creating a vibration or a phonon that super-sensitive sensors might one day be able to pick up. Another concept looks for a specific signature in the beta decay of radioactive atoms, where the presence of the cosmic neutrino background would cause a tiny, calculable shift in the energy spectrum of the emitted electrons. Successfully detecting this background would open a window to a time even earlier than the cosmic microwave background can see. It would allow us to peer directly into the universe's first second of life, testing our models of the Big Bang with unprecedented precision, and perhaps even revealing secrets about the particle nature of the neutrinos themselves, such as their exact masses and whether they are their own antiparticles. This invisible ocean is a frozen record of the cosmos in its infancy, a silent witness to the moment everything began to take shape. But the cosmic neutrino background is not the only dark relic from our fiery beginning. The search for dark matter has led to candidates across a staggering range of masses, from the ultra-light action to the truly monstrous. Imagine a single particle so heavy that its mass is comparable to a grain of pollen, a speck of dust. This is not a metaphor. A WIMP-zilla is a hypothetical dark matter particle with a mass that can reach 10 to the 16 giga-electron volts. To grasp this scale, a single WIMP-zilla would weigh as much as 10 million billion protons. These are not the lighter, thermally produced WIMP that have been the focus of decades of searches. WIMP-zillas are a different kind of beast entirely, born from the most violent and exotic processes in the early cosmos. Their production could not rely on the thermal bath of the hot Big Bang. Instead, they are thought to be non-thermal relics created in two primary ways. The first is during the period of reheating, that moment when the inflattened field decayed and flooded the universe with the hot particle soup. The collisions and interactions in this incredibly energetic plasma could have been violent enough to directly produce these super-heavy particles. The second, even more exotic mechanism is gravitational particle production. In the chaotic spacetime of the very early universe, particularly during the transition from inflation to the hot Big Bang, the violent expansion and contraction of space itself can act like a drum, beating the quantum fields and literally shaking particle pairs out of the vacuum. The immense gravitational energy of the expanding cosmos could have directly condensed into WIMP-zillas. Because they are so fantastically heavy, they would have been produced in much smaller numbers than lighter dark matter candidates. But their incredible mass means that even a tiny population would be enough to account for all the dark matter we observe. Their detection, however, is a monumental challenge. They are far too heavy to be produced in any particle collider we could ever build. Instead, physicists look for indirect signals. One possibility is that two WIMP-zillas could very rarely annihilate each other, or a WIMP-zilla could decay, producing a burst of ultra-high energy cosmic rays or gamma rays. Our most powerful observatories, like the Pierre Auger Observatory, scan the skies for these rare, incredibly energetic particles, searching for an anomalous signal that cannot be explained by any known astrophysical source. Another method involves looking for the subtle effects of such a heavy particle passing through a detector. While a WIMP-zilla would interact only extremely weakly with normal matter, its sheer mass means that if one did collide with a nucleus in a super-sensitive detector, it would deposit a significant amount of energy, creating a unique and unmistakable signal. The search for WIMP-zillas pushes the boundaries of dark matter science, forcing us to consider that the missing majority of the universe's matter might not be a sea of light particles, but a sparse population of cosmic titans, each one a fossil from the first instance of reality. Dark matter and dark energy have always been treated as separate cosmic entities, but what if they are two faces of the same mysterious substance? This is the radical proposal behind the Chaplygin gas, an exotic fluid that dares to unify the dark sectors of the cosmos. The original idea was inspired by a surprising source, the aerodynamics of air passing over an aircraft wing. The Russian physicist Sergei Chaplygin found a mathematical description for such fluids, and cosmologists later realized this same equation could describe a universe-spanning medium with a truly bizarre property. Its pressure is negative and inversely proportional to its density. In the dense, crowded universe of the early cosmos, this fluid would have had a pressure near zero, causing it to clump together under gravity just like ordinary matter. In this phase, it would have acted as dark matter, providing the gravitational scaffolding for the first galaxies. But as the universe expanded and the density of this fluid dropped, its negative pressure would have begun to dominate. Instead of clumping, it would have started to push space itself apart, behaving exactly like the dark energy we observe accelerating the universe today. One single component could have orchestrated the entire cosmic drama, first building the structures and then tearing them apart on the grandest scale. The generalized Chaplygin gas models refine this idea, allowing for a more flexible relationship between pressure and density. They paint a picture of a universe where the first gravitational seeds, the tiny overdensities that grew into galaxies, were not carved solely by cold dark matter, but by this chameleon-like fluid. As it transitioned from a clustering state to a smooth, repulsive one, it would have imprinted a unique signature on the formation of cosmic structure. This elegant unification, however, faces significant challenges. When we run detailed computer simulations of how a Chaplygin gas universe would evolve, the results clash with what we actually see. The cosmic microwave background's intricate pattern of hot and cold spots does not match the predictions well. Furthermore, the distribution of galaxies and galaxy clusters across the universe, the large-scale structure, seems to require a more traditional separation between dark matter and dark energy. The Chaplygin gas models tend to suppress the formation of structure in a way that is inconsistent with the rich cosmic web we observe through our telescopes. Despite these tensions, the idea remains a powerful testament to the quest for simplicity in cosmology, a search for one profound entity that could wear two very different masks across the lifetime of the universe. At the most fundamental level, space is not a smooth stage but a dynamic fabric woven from threads of quantum geometry. This is the world of spin networks, the core of loop quantum gravity. Picture a vast, evolving web where each link represents a tiny, quantized area and each node a discrete volume of space. These are not particles moving through space. They are the very atoms of spacetime itself, carrying information about geometry through their quantum spin. In the very early universe, this network was incredibly dense and complex, a seething foam of these elementary connections. As the universe evolved, so did this network, its nodes and links interacting and rearranging in a cosmic dance dictated by the laws of quantum gravity. This dynamic fabric leads directly to the concept of the Big Bounce. Instead of a singularity, the collapse of a previous cosmic phase reached a point where the quantum geometry could be compressed no further. The density hit a maximum, and the repulsive force generated by the quantum nature of gravity became overwhelming. This force, absent from Einstein's classical equations, caused the universe to rebound, turning collapse into expansion in a cosmic reversal we call the Big Bounce. The classical Friedmann equations, which describe the universe's expansion, are profoundly modified at this scale. Effective dynamics from loop quantum cosmology introduce a crucial correction term, a quantum bounce that naturally replaces the singular, infinitely dense beginning. It is as if the universe has a fundamental cosmic repulsion built into its quantum structure, a safety mechanism that prevents its own self-destruction. This violent transition from contraction to expansion is not a smooth, silent event. The rapid change in the geometry of spacetime acts like a giant drum, vigorously shaking all the quantum fields that exist. This process, known as particle production across the bounce, floods the reborn universe with a hot, dense plasma. Quarks, electrons, and photons are copiously created from the immense gravitational energy of the bounce itself, setting the stage for the hot Big Bang without a true singularity. The specific way the universe was shaken during this transition could have left a faint but unique fingerprint on the cosmos. The quantum fluctuations in the gravitational field, the very ripples in spacetime from the bounce, would have imprinted a particular pattern on the cosmic microwave background. Most intriguingly, this pattern might be detectable in the CMB's polarization, the specific orientation of its light waves. While inflation predicts a specific, nearly scale invariant spectrum of gravitational waves, a quantum bounce could generate a different kind of primordial gravitational wave background, one with a distinct signature in the B modes of polarization. Finding such a signature would be direct evidence that our universe was born from a rebound, a cosmic echo of a time before time, written in the oldest light we can see. The mathematical elegance of string theory opens up a cosmic landscape of staggering proportions, a vast terrain of possible realities. The specific geometry of the 6 or 7 hidden dimensions in string theory is not unique. The equations allow for a truly astronomical number of stable configurations, each one representing a different vacuum state with its own unique physical laws. This is the string theory landscape, and the number of possible vacua is estimated to be 10 to the power of 500 or more. That number is so immense it defies any human analogy. It is more than the total number of atoms in the observable universe. Within this near-infinite array of possibilities, the properties we take for granted are not fundamental truths but local bylaws. The mass of the electron, the strength of gravity, the number of fundamental forces, even the number of spatial dimensions that expanded to a large size, all of these are frozen accidents determined by which specific vacuum our pocket of the multiverse happens to inhabit. Our universe, with its specific particle content and force strength, is just one tiny garden in this cosmic wilderness. This incredible diversity presents a profound challenge for string theory as a predictive science. If the theory allows for every conceivable universe, how can it explain why we see this particular one? How do we select our vacuum from this dizzying array of options? One possible mechanism is quantum tunneling. In the chaotic froth of the early multiverse, our region of space could have undergone a quantum transition, tunneling from one vacuum state to another until it settled into the one we now call home. It was a random roll of the cosmic dice, a lucky jump into a stable configuration that allowed for complexity. Another idea is dynamical selection, where the laws of physics we observe are not random, but are the most probable outcome of some underlying dynamical process. Perhaps vacua that are supersymmetric or have a positive cosmological constant are statistically favored, naturally leading to a universe like ours. Yet, when faced with 10 to the 500 possibilities, the role of anthropic reasoning becomes almost unavoidable. This is not an explanation for why our vacuum exists, but a selection effect. We could not possibly find ourselves in a vacuum where the strong nuclear force is too weak to bind protons and neutrons, or where the cosmological constant is so large that it rips apart atoms before they can form. We can only exist in a vacuum that permits the existence of long-lived stars, stable planets, and ultimately, conscious life. The fact that we observe a universe finely tuned for complexity is therefore not evidence of a grand design, but a simple consequence of our own existence as observers. The first particles in our cosmic story, the quarks and electrons with their specific properties, were not predetermined. They were simply the ones that emerged when our local patch of reality crystallized into a hospitable vacuum, one rare possibility among an unimaginable sea of silent, barren alternatives. The decay of the inflattened field was not a gentle simmer, but a cosmic explosion. After inflation stretched the universe to its smooth, cold state, the field that drove it still held immense energy, locked away and waiting to be released. This transition, known as preheating, was one of the most violent and chaotic events in all of cosmic history. The process began as the inflattened field started to oscillate around the minimum of its potential, like a giant pendulum swinging back and forth through the cosmos. But this was no ordinary oscillation. Each swing of the field acted as a powerful, periodic pump, transferring its energy not gradually but in sudden, explosive bursts. This mechanism is called broad parametric resonance. Think of it like pushing a child on a swing. If you push at just the right moment in each swing, the amplitude grows dramatically with every cycle. In the early universe, the inflattened field was that push, and certain types of matter fields were the swing. The resonance was so broad and powerful that it could transfer half of the inflattened's energy into new particles in just a few dozen oscillations. This was not the slow, one particle at a time decay of later reheating. This was a non-thermal, explosive instability that ripped the universe out of its cold, inflationary state and filled it with a raging, turbulent sea of particles. Vast, coherent regions of space were suddenly flooded with ultra-dense concentrations of these newly created particles, far from any state of thermal equilibrium. In this chaotic frenzy, the universe did not heat evenly. The violent fluctuations in the evolving fields could have twisted and knotted themselves into stable, persistent structures known as topological defects. These are like cosmic cracks or scars frozen into the fabric of reality. Depending on the specific particle physics model, this could have created domain walls, cosmic strings, or other exotic relics, each one a fossilized imprint of the preheating turbulence. The sudden, explosive nature of this process also means it would have been incredibly loud in gravitational waves. The rapid, asymmetric motions of such immense energy densities would have shaken the very fabric of spacetime, generating a potent background of primordial gravitational waves. This specific gravitational wave signal, with its characteristic frequency spectrum, is a potential smoking gun that future observatories might one day detect, a direct echo of the universe's violent rebirth. Only after this initial explosive burst of preheating subsided did the universe settle into a more gradual and orderly phase known as perturbative reheating. In this slower process, the remaining inflaton energy decayed through more conventional particle interactions, colliding and scattering until everything reached a state of thermal equilibrium. This final phase created the hot, smooth, and uniform particle soup of the traditional Big Bang model. But those first instants of preheating were utterly different, a brief period of creative chaos that determined the initial conditions for everything that followed, setting the stage for the universe we now call home. Black holes present a paradox that threatens to unravel our understanding of reality itself. It begins with a simple question: what happens to the information describing an object when it falls into a black hole? According to Einstein's general relativity, if you were to cross the event horizon, you would notice nothing special at first. The horizon is not a physical wall. It is a point of no return, a one-way street where the gravitational pull becomes too strong for even light to escape. The principle of equivalence assures us that a free-falling observer should experience the laws of physics as they always do. But quantum mechanics paints a different, deeply troubling picture. Stephen Hawking showed that black holes are not truly black. They slowly evaporate by emitting a faint glow of radiation, now named after him. This Hawking radiation is thermal. It is random heat. It contains no information about the individual particles that formed the black hole. When the black hole finally evaporates completely, all the detailed information about everything that ever fell into it seems to have vanished from the universe forever. This violates a sacred principle of quantum mechanics called unitarity, which states that information can never be truly lost. It can be scrambled, but it must be preserved in some form. This is the black hole information paradox, a fundamental conflict between our two most successful theories of physics. One proposed solution is as radical as the problem itself, the firewall. To preserve the purity of quantum mechanics and prevent information loss, physicists Ahmed Olmary, Donald Marolf, Joe Pulczynski, and James Sully suggested that the event horizon might not be the smooth, gentle gateway of general relativity. Instead, it could be a blazing wall of fire, an intensely energetic region where any infalling object would be instantly incinerated. The firewall would act as a cosmic shredder, destroying the information of anything that touches it, but in a way that is consistent with quantum mechanics by converting it into a form encoded in the outgoing radiation. This idea, however, creates its own catastrophic problem. It violently contradicts the equivalence principle, the very foundation of general relativity. You cannot have both a smooth spacetime continuum at the horizon and a fiery death wall. One of these core pillars of physics must be wrong. This paradox forces us to confront the nature of spacetime at its most fundamental level. Is spacetime itself an emergent property, something that arises from a more basic quantum structure? The firewall proposal hints that the smooth continuity of space and time might break down dramatically at the horizon, revealing a more fundamental, discrete reality. This has profound implications for the origin of the universe. The initial singularity of the Big Bang is often compared to a black hole in reverse. If the event horizon of a black hole is a place where quantum gravity creates a firewall, then the moment of cosmic genesis might also have been shielded by an unimaginable energetic boundary. The first particles to emerge from the Big Bang may not have come from a perfectly smooth, infinitely dense point. They could have been born from the dissolution of a primordial firewall, a cosmic conflagration where the laws of physics as we know them were forged in an inferno that resolved a fundamental paradox. The information that defined our universe, the quantum states of every quark and electron, might have been imprinted in that first great blaze, a solution to a cosmic paradox written into the very first moments of time. Our smooth, continuous experience of space and time may be the universe's most convincing illusion. beneath the apparent flow of reality, the very fabric of existence could be granular, a vast collection of discrete, indivisible events. This is the theory of causal sets, a radical reimagining of reality where space-time is not a smooth stage, but a network of fundamental moments related by a single, simple rule: causality. In this picture, the universe is a set of elements like individual grains of sand, with a partial order defining which events can influence which others. If one event can send a signal to another, they are causally linked. This structure, this web of cause and effect, is not embedded in a pre-existing spacetime. It is spacetime, the entire four-dimensional continuum of our experience, its geometry and even its dimensionality, emerges from the complex pattern of connections within this cosmic network. Because this theory is background-free, it does not rely on a predefined stage for the universe to play out upon. The stage itself is built from the relationships between the actors. This has a profound consequence for the origin of the universe. The Big Bang Singularity, that point of infinite density, simply cannot exist. There is no continuum to become infinitely curved. The causal set has a finite number of elements at any stage, so density has a natural maximum. The beginning of our universe would not be a singular point, but a minimal set of foundational events from which all others have causally descended. This discrete nature also provides a natural solution to one of the most vexing problems in physics, the infinities that plague quantum field theory. When calculating the properties of particles, physicists often get absurd, infinite results because they assume space is infinitely divisible, allowing for fluctuations on arbitrarily small scales. In a causal set, there is a fundamental cutoff, a smallest possible scale set by the density of the elements. This acts like the pixel size on a screen, eliminating the nonsensical infinities and providing a finite, computable foundation for all of physics. But how do the particles we know and love, like electrons and quarks, emerge from this causal web? They are not fundamental ingredients. Instead, they are persistent patterns, specific vibrations or excitations that propagate through the network. Think of a soliton, a stable, self-reinforcing wave that can travel through a medium without losing its shape. An electron could be such a stable disturbance, a particular pattern of causal links that moves through the set, maintaining its identity and properties over time. Its propagation is dictated entirely by the underlying causal structure. Where it can go next is determined by which new elements are in its causal future. This means that the speed of light, the maximum rate of causation, is not a law imposed on space. It is a direct consequence of the network's connectivity. For the early universe, this framework paints a stunning picture. The cosmos began not as a hot, dense fireball, but as a sparse, rapidly growing causal set. The Big Bang was the moment of maximum growth, a quantum nucleation of new elements and their causal relations. The familiar expansion of space and the hot thermal state of particles would both be derived phenomena, emerging as the set grew in complexity. This approach dares to do what few others can, derive the cosmological parameters we observe, like the cosmological constant, from first principles. The specific dynamics of how the causal set grows could naturally lead to the tiny, positive value for dark energy that we measure, not as a mysterious accident, but as an inevitable outcome of the universe's discrete causal architecture. This is a vision of a universe built not from stuff, but from relationship and information, where time is born from order and space from connection. Gravity has always been the odd force out. While the other fundamental forces are explained by the exchange of particles, gravity is described by the bending of space-time itself. But what if this bending is not a fundamental property of the universe? What if gravity and even space and time are not the bedrock of reality but secondary phenomena, emerging from a deeper, more fundamental layer? This is the radical proposal of emergent gravity, a paradigm shift that reimagines our cosmic foundations. The clues for this idea come from an unexpected place, the physics of black holes. Stephen Hawking's work showed that a black hole's entropy, its information content, is proportional to the surface area of its event horizon. This was a profound hint. In thermodynamics, entropy is a measure of the number of microscopic states in a system. For a gas, it emerges from the random motions of countless molecules. The fact that a black hole's information is stored on its boundary suggested that space-time itself might be like a gas with its properties, including gravity, emerging from the collective behavior of countless underlying microscopic components. Think of the surface of a pond. Its smooth, fluid nature emerges from the frenetic interactions of trillions of water molecules. You do not need to know about individual H2O molecules to describe a wave. You can use fluid dynamics. In the same way, emergent gravity suggests that Einstein's general relativity is like the fluid dynamics of spacetime, a powerful but approximate description that emerges from a more fundamental quantum reality. The engine of this emergence appears to be quantum entanglement. In the quantum world, two particles can become entangled, their fates linked regardless of distance. This spooky connection is now seen as a fundamental resource that might actually weave the fabric of space itself. The proposal is that every point in space is connected to every other point by a vast, dynamic web of entanglement. Where entanglement is strong and dense, space exists. Where it is absent, space simply falls apart. In this view, gravity is not a force in the traditional sense. It is an entropic force. A brilliant analogy is a polymer chain. If you take a tangled mess of polymer chains and pull on one end, it will resist. This resistance is not due to a fundamental force, but to the statistical tendency of the system to move toward a state of higher entropy, greater disorder. The polymer wants to remain tangled. Pulling it straight reduces its entropy, so it fights back. Physicist Eric Verland proposed that gravity is exactly this kind of effect. When a massive body sits in space, it effectively displaces some of the microscopic degrees of freedom, creating a kind of entropy gradient. When another object moves close to it, it feels a tendency to move toward the region of higher entropy, much like the polymer resisting being straightened. This tendency is what we perceive as the attractive force of gravity. It is not a force pulling on the object, but a statistical push toward a more probable configuration of the underlying microscopic system. This entropic approach leads to a stunning explanation for one of cosmology's greatest mysteries, dark matter. In the emergent gravity paradigm, dark matter might not be a substance at all. There may be no invisible sea of exotic particles. Instead, what we call dark matter could be an apparent effect, a mismatch between our fundamental understanding of gravity and how it truly emerges. In the outskirts of galaxies, where the visible matter thins out, the standard laws of gravity predict stars should orbit more slowly than they actually do. We invented dark matter to provide the extra gravity needed to explain these rapid orbits. But if gravity is emergent and entropic, its equations are modified on large cosmic scales. The extra gravitational pull we attribute to dark matter could simply be a consequence of the changing entropy content of space itself in these low-density regions. The gravity we measure is there, but its source is not a particle. It is a signature of the way information and entanglement are structured in the cosmos. This reframes our search for the first particles in a dramatic way. If spacetime and gravity are not fundamental, then the singularity at the Big Bang was not a real point. It was a place where our emergent description broke down completely. The first particles did not appear within a pre-existing spacetime. They co-emerged with it. The quantum fields that gave rise to quarks and electrons and the geometry of the universe itself both crystallized from the same underlying entangled quantum system. The initial conditions of the universe were not set on a spacetime stage. They were the first stable patterns to form in a primordial sea of information, a cosmic phase transition where both stuff and space were born together. This staggering mismatch represents the single greatest failure of theoretical prediction in all of science. Quantum field theory, our most successful framework for describing particles and forces, tells us that empty space is not empty at all. The vacuum is a seething, bubbling sea of temporary activity. Virtual particle pairs constantly wink into and out of existence, borrowing energy from the void for a fleeting moment before annihilating each other. Every possible vibration of every quantum field contributes a tiny bit of energy to this underlying hum. This is the zero-point energy of the universe, and when physicists calculate its total density to predict the cosmological constant, the result is a number that is 1 followed by 120 zeros too large. It is a value so catastrophically immense that, if it were accurate, the repulsive force would have ripped every atom apart before the first stars could ever form. Our universe, in essence, should not exist. The fact that we are here to measure a tiny, positive cosmological constant means that something is profoundly wrong or missing from our picture. One proposed fix is supersymmetry. If every particle has a superpartner, the positive energy contributions from fermions and the negative contributions from bosons could perfectly cancel out, driving the net vacuum energy to zero. But we know supersymmetry, if it exists, must be broken. The superpartners are not massless twins, so the cancellation cannot be perfect. It would have to leave behind a remnant exactly 120 orders of magnitude smaller than the initial calculation, a level of fine-tuning that feels just as miraculous as the problem itself. This leads to the stark possibility of the anthropic multiverse. In a vast landscape of universes, each with a randomly selected cosmological constant, only the incredibly rare bubbles with a value as small as ours could ever give rise to galaxies and life. Our existence is not evidence for a unique theory, but simply a selection effect. We could not find ourselves anywhere else. Other ideas are even more radical, suggesting that gravity simply does not feel the vacuum energy in the way we think. A degravitation mechanism might exist where the cosmological constant is large, but gravity filters it out on the largest scales, making the universe effectively blind to its own immense vacuum energy. Solving this problem would force us to redefine nothingness itself. The vacuum state from which the first particles emerged would be understood not as a featureless void, but as a state of precise, balanced tension. The genesis of every quark and electron was played out on a stage whose fundamental energy was set by a deeper principle we have yet to uncover, a cosmic coincidence that is the silent, invisible bedrock of all reality. The staggering fine-tuning of the cosmological constant points to a cosmos balanced on a razor's edge, a reality so improbably perfect it begs for an explanation beyond pure chance. This leads us to the final and most speculative frontier, the possibility that our entire universe is a numerical simulation running on a computer of unimaginable power. The argument is not based on science fiction, but on a simple logical projection. If any civilization, anywhere, ever reaches a post-human level of technological maturity, it would possess computing resources so vast that running detailed simulations of its own history, or even entire universes, would be trivial. There could be billions of such simulated realities for every one base reality. Statistically, we are far more likely to be in one of those countless simulations than in the original. In this view, the laws of physics are not fundamental truths, but the high-level programming rules of the simulation. The smooth continuity of space and time might be an approximation, an emergent property of a discrete underlying lattice. This is not so different from the way a digital screen creates the illusion of a seamless image from finite pixels. Theories like lattice gauge theory, where space is modeled as a discrete grid, could be more than just a mathematical tool for physicists. They might be a glimpse into the actual source code of our reality. So what would the first particles be in such a simulated cosmos? they would not be tiny specks of matter or energy. The true fundamental building blocks would be bits, or more accurately, quantum bits, qubits of information. A quark or an electron would simply be a stable, persistent pattern of information processing within the cosmic computer's memory. Their properties, their masses and charges, would be the variables assigned to them by the simulation's programming. The Big Bang would not be the ignition of a physical fireball, but the instant the program was executed, the moment the initial conditions were loaded and the first lines of cosmic code began to run. This idea forces us to confront profound philosophical questions. Is our consciousness just a complex algorithm running on this celestial hardware? Could we ever find evidence, a glitch in the matrix? Some have suggested we might detect signatures of the underlying computational lattice in the highest energy cosmic rays, a slight directional preference in space that betrays the grid structure. Or perhaps the finite precision of the simulation would manifest in subtle inconsistencies in the laws of physics at the most extreme scales. The simulation hypothesis reframes our entire quest. The search for the first particles becomes a search for the universe's fundamental data types, and the theory of everything we seek might not be a set of physical laws, but the user manual for the system we are running on. Our cosmic journey through 30 incredible theories has reached its end, from the singular spark of the Big Bang to the possibility of a simulated reality. We have stood at the edge of the Planck Epoch, witnessed the birth of matter from a 1 in a billion asymmetry, and questioned whether our universe is a hologram, a bounce, or a collision of unseen dimensions. While the ultimate truth of the first particles remains just beyond our grasp, the quest itself is a testament to something extraordinary. It reveals the profound creativity and relentless curiosity of the human mind, forever pushing against the boundaries of the unknown. Each theory, from the mathematically rigorous to the philosophically daring, offers a unique window into the dawn of time, a different story of how something came from nothing. These are not just abstract ideas, they are the narratives we use to find our own place in the vast, unfolding cosmos. So we leave you with a final question. Which of these cosmic origins resonates most deeply with you? Does the elegance of supersymmetry speak to you, or the cyclical poetry of conformal cycles? Perhaps the radical simplicity of emergent gravity captures your imagination. Share your thoughts in the comments below and let us continue this grand conversation together. Thank you for exploring the deepest mysteries with us. For more journeys to the edge of understanding, be sure to